All right, let's get started. Hello, good morning, everybody. Thank you for braving the crazy cold temperatures to get to class today, and welcome to everybody joining through the live stream. I hope you guys are having a good first week and that you are enjoying all your courses and things like that. Couple quick announcements. So just as a reminder, our first homework sets are due on Sunday night through Wiley Plus. If you need help on those, there's drop-in help tonight as well as on Sunday, and those times are posted with their Zoom links on Moodle. There's also going to be an algebra review tonight at 5 o'clock. That link is posted in Moodle, and that will be repeated on Monday at 4 o'clock. So if you did the algebra assessment and you think you could use a little brush up on some of your algebra, that will be a great workshop to attend. We'll also post a video recording of that workshop on Monday night, Tuesday morning, depending on what it processes, so that if you're not able to attend, you can still access that. So that, in addition to the 1.3 mini quiz, that's our first graded quiz, will be due by Sunday. You don't have to wait till Sunday to take it. It's open now. So after class today or tomorrow, anytime, you just have to find a 15-minute period. Again, it's 3 questions, multiple choice, to log in and take it. So that's about it for the announcements. Hopefully you saw in Moodle all the times and links to the different drop-in help, so that as you are working through things, if you need help, you can just log in and see when someone is available to help you. So today we're going to start what's called rates of change, and there's 2 different types of rates of change we're going to talk about. The majority of the focus will be on what's called the average rate of change. We will use that like 95% of the time, and then at the end we'll do at least one example of relative rate of change, just so we understand what the difference is. Okay, so I'm going to switch over to the dot cam now. All right. So sort of big picture for a minute, we are enrolled in a calculus class, right? So what is calculus? So calculus is considering how things change, okay? So calculus 1 looks at rates of change. So we're interested in how quickly does a function change, in which direction does it change, sometimes why is it changing? So very, very condensed, calculus is the study of change. Okay, so what we're going to be doing is we're going to be building a foundation of how we think about different types of rates of change, what we already know, how we can use what we know to figure out what we don't know, and then how do we make it better, sort of our big path process. And so the one thing that you are assumed to know for this class is the one rate of change that you've probably seen a million times in your life, which is a linear function. Okay, so linear functions are typically written as y equals mx plus b, right? And so you may have seen it as y minus y1 equals m times x minus x1, or some other rewritten version, which is the same. But a linear function has a rate of change built into it, which is the slope. Okay, so slope is where we sort of start building from. So as a reminder, slope is going to be the change in y over the change in x, which tells us how much the dependent variable changes for every 1 unit the independent variable changes. And there's a lot of ways that people think about and write slope. So you might have something like the change in y over change in x. You might have something like y2 minus y1 over x2 minus x1. You may have heard something like rise over run, right? These all are ways to think about slope. And so slope is going to give us the rate of change of a line. Okay, so it tells us exactly how much we will change in the y direction for every unit we move in the x direction. So that is the rate of change that we know is slope, right? And again, we get that from a linear function by doing one of these calculations, change in y over change in x. So what we do now is we say, okay, we know how to find the rate of change of a linear function. But what do we do if we have a function that is not linear, right? So we have some sort of curved function. How do we think about and talk about how this function changes? We don't have a way to get slope on a line that's curved. Okay, now there are ways to do this geometrically, but we are not in a geometry class, so we are not going to consider things like arc length or geometrical representations, although that could be a way to think about it. Okay, instead, we're going to say, okay, well, if we want to know how much the function changes, we want to know, one, where we are interested in looking, right? So with our approach coming up, we are going to look between 2 points. Okay, we are going to ask how much does this function change between this point and this point, right? And then if we can do that for any 2 points, we can kind of look at a whole entire function. And so what we're going to do is we are going to consider using a line to help us understand how much a curved function changes, because we know about lines, right? So we're going to use what we know to try to figure out what we don't know. So what does this process look like? Okay, so let's consider an example where we are interested in how much this function changes between x equals 1 and x equals 3. Okay, so we want to know how much does this function change from 1 to 3. So for 1, if I go up here, and then 3, I go up to here. So I'm interested in how much this function changes from here to here. Okay, now that is the ultimate goal, and we don't have enough tools to figure it out exactly yet, the rate of change. That's what we're trying to build up to, the rate of change. So what we do is we say, well, we know how to find slopes of lines, so why don't we go ahead and connect these 2 points with a line, right? What will that tell us? It'll tell us how we would get from here to here if this part had been linear, right? Because we know that we're starting here and that we're ending here. That's true no matter what. But we're changing what happens in between. So we're not finding the rate of change. We are finding what's called the average rate of change. So it's an approximation of how much our function changes, which is the best we can do right now because the only tool we have is lines, right? So the average rate of change is the slope of the line that connects the 2 points that we are interested in, okay? Now, as I mentioned before, there's a lot of ways to write slope, but the way that we are going to look at it in this class, okay, we're going to change in y over change in x, but when we talk about the change in y, we are going to use functional notation, and I'll show you what that means. So the y value at 1, we are going to call f of 1, okay? And the y value at 3, we're going to call f of 3. And all that means is that we are plugging 1 into the function to get the corresponding y value, which we're going to approximate in a minute. So if we wanted to get the slope of this line, the way we could write this is f of 1 minus f of 3 divided by 1 minus 3. Okay, so this is how we're writing the y values. So change in y over change in x. That's how we can write the slope of this line. Okay, so now we would need to approximate those values. So for f of 1, I would come up, I'd look over here, I'd try to approximate about where it is. It's between 2 and 3, but closer to 3. So I'm going to call that 2.8. F of 3 is a little bit above 1 over here on the axis. So I'm going to call that 1.3. Okay, your approximations don't need to be perfect. We could have done 2.9 and 1.2, but we should be in the ballpark. And now 1 minus 3 is going to give me negative 2. Okay, so now when we crunch that number, we get negative 0.75. So what does that mean? Okay, so I'm going to say slope is approximately negative 0.75. That means that my function changes on average by 0.75 in the downward direction for every 1 unit I move in the independent direction, right? So if I move 1 unit here, I go down 0.75. I go 1 unit, down 0.75, right? So it's the same as we normally think about slope. I want to point out that I was expecting my slope to be negative because my line is going down from left to right. And if a line is downward sloping, then the slope is negative. So this is how we're going to approximate the rate of change for now, right? The first goal is to fit in what we know how to do, and then later we'll try to make it better, okay? So this process, like I said, we're finding the average rate of change. So the general formula to write this that we'll use, okay, is that we are going to be using A and B as our generic points that we're looking between. So A and B are the 2 points between, I don't want to say between, are the 2 points we are looking between. Okay, so A and B can be any numbers. In the last example, it was 1 and 3. So then we can write our formula as f of B minus f of A over B minus A. Okay, which again is just one way to represent slope. We're looking for the slope of the line between 2 points. Now, I want to point out, just in case you're unsure about this, it doesn't actually matter if you pick your A to be 1 or 3, right? As long as you are consistent within the formula. So we could have done this as f of 3 minus f of 1 over 3 minus 1. As long as you are consistent, you get the same answer. I always pick my B to be the bigger number. I just do B for bigger. But again, it doesn't matter which one you pick to be A and which one you pick to be B, as long as you plug it in consistently. Okay, so what do we want to do with this, right? We want to look at different functions, figure out how to get the average rate of change between points. And so we're going to start with some graphing here. So this is the same picture we were just looking at, and we approximated this first one to be negative 0.75. But now we want to look at 2 more rates of change. So if we change where we are looking, the rate of change is going to change itself. So we are going to look at the average rate of change from x equals 0 to x equals 2. That's one we're going to try to approximate. This line is going up, so I'm expecting the slope to be positive. And then we're also going to try one where we look at x equals 0.5 to x equals 4.5. Okay, so that's going to be this line. I'm going to try to draw this really super straight on top. So we have a good visual representation. Okay, so what I would like you to do is I'd like you to take 2 minutes and see if you can approximate what the slope of the line's going to be between 0 and 2, and also between 0.5 and 4.5. We're expecting the 0, 2 to have a positive outcome, and I'm expecting the second one to have a negative slope. Okay, so again, change in y over change in x, so you're approximating the values. They don't have to be perfect, right, because it's an approximation, but we should end up in the same ballpark once we go through it. So take about 2 minutes. The TAs will walk around if you have any questions, and then we'll go through it together. Okay, take about 30 more seconds to finish up whichever one you're working on. All right, so for the first one, for the blue line, we're trying to find the average rate of change from 0 to 2. So the way we would write the formula, we can write f of 2 minus f of 0 over 2 minus 0, or you can write f of 0 minus f of 2 over 0 minus 2. So now f of 2, we're trying to approximate the value at 2. So we come up here, we look over towards the y value. That to me looks about the same as the last one, so I'm going to call that 2.8. Again, you may have called it 2.9, 2.7, somewhere in that ballpark. That's totally fine, but you shouldn't have something like 15, right, which is not even on the axis. It should be somewhere between 2.5 and 3, right? And then minus f of 0, so I come over here, and it looks like this touches right at 1, so I'm going to call that 1 divided by 2. So I crunch that number, and I'm going to get 0.9. As I mentioned before, I expected the slope to be positive. This number is positive, so that's good. So my slope is approximately 0.9. So my average rate of change from 0 to 2 is 0.09. Now, for the second one, I'm expecting my slope to be negative because we are downward sloping. So I start with my formula. So f of 4.5 minus f of 0.5 divided by 4.5 minus 0.5. So f of 4.5 means that we are going to our 4.5 and we are coming down and we are looking at the value. To me, that looks like -1 minus, then 0.5. We come over here, we're going to go up until we touch the graph. That looks like it's right about 2. And then on the bottom, we have 4.5 minus 0.5, which is 4. So be really extra careful with negative numbers. If you're more comfortable using your calculator to double check, that's fine. And so here, when we crunch this number, we get -0.75. Okay, so here we are expecting a negative number, We got a negative number, so that's good. And you'll notice that that's the same value we got when we did this first one on the prior problem. And when you look at the lines, that kind of makes sense because they look parallel, right? And we know that parallel lines have the same slope. So that means that we're probably on the right track here. So when we do this process, right, when we say, okay, we want to figure out how much a function is changing on average, we're going to use a line to approximate. When that happens, that line has a special name, okay? And so when we do that, this line is called the secant line. So a secant line is a line that connects 2 points on a nonlinear function, okay? That's the name of this line that we're putting in. The slope of the secant line gives us the average rate of change, okay? So there's 2 types of lines we'll name in this course. So this is the first one. So we have generic linear functions. That's what you already know. Secant line has a special meaning. It means it connects 2 points, okay? So that's how we start thinking about this and how we visualize this on a graph. But how are we going to use average rates of change in other types of situations? So we want to remember the formula, and now we want to start applying it to other of our model types. So we're going to start with a formula here. So we want to find the average rate of change between 1 and 4 for the function y equals f of x equals x squared plus 3x minus 1. So what we need to do is we need to remember the formula f of b minus f of a over b minus a, and think about how we find the y values when we have a formula instead of a graph, okay? So I'm going to give you 1.5 minutes. Okay, see if you can write out the formula. Remember, your A and your B are given up here, so between 1 and 4. And once you have your formula written out, think about how we can use this formula to actually get the numbers we need to answer the question. Okay, so take about 1 to 2 minutes, see what you can work out, and then we'll go through it together. All right, so let's take a look at this one. So again, we know we're looking between 1 and 4. So when we set up our formula, we're going to have f of 4 minus f of 1 over 4 minus 1. That represents the slope of the line that connects 1 and 4. So now we have to ask ourselves, how do we find f of 4? When we had a graph, we just approximated it from the graph. Here we have a formula, so we need to do that calculation by plugging the 4 into the given function. So 4 squared plus 3 times 4 minus 1, right? So we have 16 plus 12, which is 28, minus 1 is 27. So f of 4 equals 27. So 27 minus, we're going to do the same thing for f of 1. So 1 squared plus 3 times 1 minus 1. That's going to give us 3 divided by, now on the bottom we have 4 minus 1, which is 3. So when we crunch this number, we get 24 over 3, which is 8. So the slope of the line that connects these 2 points on this function, the slope is 8. So our average rate of change is going to be 8. So we can take our formula and retrofit it to this type of function, right? Even if we can't see what the slope is going to look like, we can still do the calculation. Okay. So as you can imagine, we are going to try to now fit this to a table. This is sort of our next attempt here. So suppose that we have a table that is continuous and it gives the data of a population P in thousands measured in years T since 1970. So what does that mean? So for example, here, let's look at this point 3085. The population is 85,000 because given in thousands. And this is 30 years after 1970. So this is the year 2000. Okay, so there's 3 questions that we're trying to answer. The first one is just like a thinking type question, and the second 2 are directly about average rates of change. So part 1 is what is the population in 1970? So thinking about how we take the information from the table to answer that question. And then for 2 and 3, we're looking for average rates of change. For 2, we're looking between 1970 and 2000. So we have to figure out how those years correlate to the table. And then for part 3, average rate of change between 1980 and 2010. So same idea, we should figure out where that information is on the table, and then we'll be applying our average rate of change formula. And so I'll just write down the formula again real quick up here. So f of b minus f of a over b minus a, that's our generic formula. So think about how we can fit it here. So I'm going to give you about 3 minutes. I want you to try to answer these 3 questions. Feel free to talk to someone next to you. The TAs will come around and then we'll go through it together.
Yeah. Yeah.
All right, take about 30 more seconds. All right, so let's go through these. So the first question asks, what was the population in 1970? So what we need to look for here is time equals 0 since t is in years since 1970. So if we want to know what's happening in 1970, we're really interested in what's happening at time equals 0. So the population when time equals 0 is going to be 60,000. So you can either write 60 and then the word thousand, or you can write the number out as 60,000, means the same thing. But that's going to be the population, right, in 1970. So this represents what's happening in 1970. Now, since we're going to be dealing in years later, we can go ahead and write the years down the table so we know what we're looking at. So 10 years after 1970 is 1980, 20 years is 1990, 30 years is the year 2000, and then 40 years is 2010. Okay, so those are the corresponding years if we convert the years by using it in relation to 1970. Now, for number 2, we want to know the average rate of change from 1970 to 2000, right? So we are looking between these two numbers. So if we wanted to write the formula for this, we could write something like P of 30 minus P of 0 over 30 minus 0. That's one way we could use it, by using the times that are here. You could write something like F of 19 or F of 2000 minus F of 1970 over 2000 minus 1970. That's going to be the same thing. But we should have some representation of the Y values over the X values. Okay, so the population after 30 years, which is the population in the year 2000, we come down to the dependent value, and that's 85. And then P of 0 is 60 divided by 30. So that's going to give us, I'm going to leave a little space because I'm going to talk about units as well. So 25 over 30, which is going to give us 0.833 repeating. Now let's talk about what the units are of this calculation, right? So the number on top is representing thousands of people, right? So 60,000 people, 65,000 people. So this is 1,000 people. And then down here on the bottom, this represents a number of years, right? So after 0 years, 10 years, 20 years, how long are we looking for? So this is 30 years. So when we talk about this number, 0.833, this is 1,000 people per year, which is helpful because we don't love decimals when we talk about people, right? So we can write it like this with the word 1,000 in the units, or we could multiply this number by 1,000, right? So that would give us 833 people per year, right? If we multiplied by 1,000. And so that tells us that the population is increasing by that many people every year between 1970 and 2000 on average. Okay, so that doesn't mean that there's 833 people every single year exactly. One year might have 800, one year might have 900, but when you consider all of those numbers, the average number is the 833. Okay, so we're going to do something similar for part 3. So now we're considering what's happening in 1980 and in 2010. So that means we're going to be looking for P of 40 minus P of 10 over 40 minus 10. And again, I'm getting those numbers by looking at what's happening in 2010. That was time equals 40. That's where I got the 40. Again, you could write something like P of 2010 minus P of 1980 over 2010 minus 1980. That'll give you the same results, right? So P of 40, right? The population was 100. And then P of 10, we come over here, we have 65 divided by 30, right? Again, we're going to crunch those numbers. So we have 35 over 30, which is 1.167 thousand people per year. Okay, so when we do average rate of change on a table, we need to figure out what 2 points on the table we're using. And then again, we're doing the change in Y over change in X. We actually tend to do this on a table fairly often in this class. We do average rates of change and other types of rates of change. So we want to get really comfortable looking at tables and finding the right information. Okay, so now we're going to flash forward real quick and do one more practice problem on a graph. We started with a graph. We're going to do another graph to make sure we remember what we're trying to do here. I realize the numbers are teeny tiny small, so I will tell you this is 1, 2, 3, 4, and then over here, 1, 2, 3. And so we just have a picture of a function in black, and we are trying to figure out the average rate of change from 0 to 4. So I've drawn in the line that connects them. I just want you to take a quick minute to approximate the average rate of change just to get another piece of practice on a graph. So I'll give you 1 minute, see if you can write out what the formula is going to look like and then what your approximation is based on the values you see here, and then we'll go through it together. So this one will be a little fast, so just try your best, and then we'll do it in about a minute. All right. So again, we're interested in looking between 0 and 4. So we have f of 4 minus f of 0 over 4 minus 0. So f of 4, we go to the 4 on the x-axis, and we go up to see what the y value is. It looks like it's right on the axis, which is going to give us a 2 minus. Then we have 0 here. It looks like it's right at 0, 0 divided by 4. So we end up with 2 over 4, which is 0.5. And I expected the slope to be positive because that line is going up from left to right. So I'm happy that I ended up with a positive number. Okay, so now we've looked at graphs, we've looked at a formula, we've looked at a table. So the next thing we're going to do is we're going to try to do an application here, which means we're going to be looking at some word problems, seeing what we can figure out. But in order to do this, this is the first time we're going to talk about physics. And so we're going to introduce some terms because there's no expected knowledge of physics in the course. So I want to make sure that we understand what these things mean in the right context before we try the problem. So the first word that we have to talk about is distance. So when you hear the word distance, we are talking about the measured length between two positions. So your distance from your seat to the screen might be 20 feet, right? So your position, the screen's position, the difference between the two, that is what we're talking about when we talk about distance. We're talking about position and the distance between two positions. We commonly use S of t when we're talking about position or distance, okay? Velocity is the other term we need to know, and that is the rate at which your position is changing. Okay, so if you're driving in your car and you're going 60 miles per hour, that is a velocity because your change in position is 60 miles over how long it takes, which is 1 hour. So when we talk about velocity, we are talking about approximating the rate of change. So what we're going to be looking at in this example is we are going to try to approximate the average velocity, which is an average rate of change. So we are going to be trying to find that by doing what we were doing in the previous problems and thinking about the original function, where we're interested in, and using our average rate of change formula. So there's two parts to this problem that we're going to look at. The first part says, suppose the position of an object falling off of a building can be found using the formula S of t equals 2,704 minus 16t squared, where position, S of t, is measured in feet and time t is measured in seconds. There's two things we want to find. First, we want to find the time when the object hits the ground. So this part is where you're really thinking about what the words in the problem are telling us, what we know, what we're trying to find, how do we figure out what we need to know, what do we know about parts of this problem, trying to put that all together. This is more of a critical thinking piece. And then the second part is to find the average velocity of the object from time equals 3 to time equals 6. So this is where we're applying our average rate of change formula in conjunction with the position formula to figure out how quickly it is changing. Okay, so I'm going to give you 2 to 3 minutes to try to work out these two pieces, see what you can figure out. Definitely feel free to talk to someone near you or ask a TA as they walk around, and then we'll go through it together. Okay, take about 30 more seconds. All right, so the first part of this question asks you to find the time when the object hits the ground. That says to me that we are solving for t. We are trying to figure out what t is. And I want to remind you that in this problem, we only know two things. We know position and we know time, right? Those are the two variables we're talking about, which means that if we are trying to solve for time, we need to know something about position. Okay, so I'm drawing a picture here of what I think is happening. That helps me try to understand what I know and what I'm trying to figure out. If I think about the moment that this object starts falling off the building, that position is going to be the position when time equals 0. So if I were to plug a 0 into this function, the position here would be 2704 feet. That's the position of the object. It's 2,704 feet off the ground. I want to know the time when the object hits the ground. So thinking about it in relation to the building, when the object hits the ground, it will be 0 feet off the ground. So the position when we hit the ground will be 0. So that means I can plug a 0 in for the position piece of the equation, and that will allow me to solve for t, which will answer the question when. Okay, so what I'm going to do is I'm going to bring this 16t squared to the other side by adding it to both sides. Okay, then I'm going to divide both sides by 16. And then I'm going to take the square root of each side, because I have t squared equals 169. When I take the square root, I get plus or minus 13. Now I need to think about if both of these answers make sense, right? Time could be 13 or time could be negative 13. We're talking about something that's happening in the physical world. So negative 13 seconds doesn't make sense. Typically, when we're talking about time, we don't have negative time, right? So that means t equals 13 seconds makes the most sense here. So the object is going to hit the ground after 13 seconds. Okay, so that's the first part. The second part says find the average velocity of the object from t equals 3 to t equals 6. So I want to know how quickly this object is falling between these two times. So again, I can retrofit this into my formula. So s of 6 minus s of 3 over 6 minus 3. Why am I using s instead of f? Because s was the governing function here. If you wrote f of 6 minus f of 3, it's the same thing, right? I'm just trying to be consistent within the problem. So here, s of 6 means I'm going to take a 6 and plug it into my function here. When I did that, I got 2128. Then I'm going to plug in a 3 into this function here. I did that on my calculator, and I get 2380 divided by, and now on the bottom, I have 3. Now, before I crunch that number, I want to remind you what the units are here, right? So on the top, we were talking about positions, and the positions were measured in feet. So we had feet on the top. And then on the bottom, the 6 and 3 were times that were given in seconds. Okay, so now when we crunch this number in our calculator, we are going to get negative 84 feet per second, right? Because feet was on top, seconds were on the bottom. That means that as this object is falling, it falls 84 feet every second that it falls between time equals 3 to time equals 6 on average, right? The negative in physics is going to indicate a direction. So that's the downward direction. And that's how much it's changing each second on average. Okay. So again, if you see the word average within a word problem, you should think average rate of change. So even if you hadn't heard the word velocity before, you do know average rate of change. We do have the two numbers and a formula, so we could certainly still figure this out without knowing anything about physics. Okay. So the next sort of way that we're going to use average rate of change is something that we're going to use pretty consistently throughout the course. And it has to do with graphing and evaluating graphs. Now, the analysis that we do on graphs and shapes of graphs is going to become incredibly important to us at the end of chapter 2 and then carry through for the rest of the course. And so I want to take a brief second to just remind you of the three, well, not remind you, one of them's new. So there's 3 ways that we classify what's happening on a graph, okay? The first is whether it's positive or negative. So we talk about that in terms of relation to the x-axis. If your function's above the x-axis, it's positive. If it's below the x-axis, it's negative. Okay. The second way is increasing, decreasing. If we go up from left to right, your function's increasing. If we go down from left to right, we are decreasing. Now, the third way that we describe a function is what we're going to talk about now. You may have heard this before, but you may not have. And that is called the concavity. So the concavity of a graph talks about how it bends. Does it bend upward or does it bend downward? So linear functions have no bend and no concavity. And so we're considering things that are not linear. So if a function bends in the upward direction, so it looks like a cup or a U shape, we call that concave up. So how does that relate to average rate of change? It turns out that if you were to take the average rate of change between points and you were to move from left to right, just calculating average rates of change, when those average rates of change are increasing from left to right, then your graph is concave up. So here's an example. So this average rate of change right here is -5. Then I move to the right a little bit and do another one. I get -3, then -1, then +3. Those numbers are increasing, right? They're becoming less negative and then become positive. So if your average rates of change from left to right are increasing, then your graph is concave up. Now, why would that be useful? If we have a picture or a graph, you can visually tell where something is concave up by looking at the bend. We are going to be mostly using this on tables where we don't have the picture, okay, just for some context. Now, as you can imagine, if our average rates of change are decreasing from left to right, so here's an example of that. So 5 and then 3 and then 1 and then -1, those values are going down, they are decreasing. If your average rates of change are decreasing, then your function is concave down. So concave down looks like a hill or a frown, we're bending downwards, okay? So we are going to be using average rates of change to determine the concavity of functions when we don't have the picture. If we have the picture, you can just look at the picture and see if it's bending up or down. You don't have to calculate average rates of change. But when we don't have the picture, our pictures that we try to draw are typically unreliable. So we want to rely on average rates of change to help us determine concavity when we don't have the picture. Okay, so let's do an example of this so we can see how this comes into play. So assume that the function below is continuous. Determine where the following function is likely to be concave up and concave down. Okay, so what we want to do is we are going to approximate the average rate of change between every 2 points as we move from left to right. Okay, so for example, the first average rate of change, f of b minus f of a over b minus a, is change in y over change in x. So we'll do 12 minus 10 divided by 2 minus 0, right? So that's going to be 2 divided by 2. That's going to give me an average rate of change of 1. So we're going to do that for every single point. And then we're going to look at if those average rates of change are increasing or decreasing. When they are increasing, our function's concave up. When they're decreasing, our function is concave down. So I would like you to take 2 minutes to calculate these average rates of change. We do these a lot on tables, so it's good practice. And once you have them all, then I want you to determine where are they increasing and where are they decreasing. All right, so take about 2 minutes and then we will go through them together. Okay. So let's take a look at this one. So again, we're just calculating the average rates of change down the table. So 2, this one will be 3, 4. So for example, this one we would do 35 minus 30, which is 5, divided by 10 minus 8, which is 2, 5 divided by 2, 2.5, right? So that's what we're doing between all of these points. Okay, so change in y over change in x between all the points on our table. We're considering what's happening from left to right. So again, we're looking for increasing and decreasing. So I notice that here, from 1 until approximately here, these values are increasing, right? From 0 to 6, x equals 0 to x equals 6, the average rates of change are going up, right? But then from here to here, we are decreasing, right? Because we have 4, 2.5, 1.5, 0.5. Those are going down. So the relationship is that when we are increasing, the function is concave up. So from 0 to about approximately 7, right? In between 6 and 8 is where we turn around. Our function, we expect it to be concave up, right? It bends upwards. But then it's going to turn around. And from 7 to 14, we will be concave down, because those average rates of change are decreasing. So that creates that downward bend. So as I mentioned, this is something we're going to do quite often on tables. So we want to get really good at approximating the average rate of change and then looking for where it's increasing and decreasing. This is something that we build onto and we do quite a bit in this course. But this is like our first go at it. So we don't need to be super good at it yet, but we're starting to practice it as we go. Okay. So as a reminder, we're going to use average rate of change to figure out concavity when we don't have the picture. Okay. If we do have the picture, we can use visual cues to help us describe what's happening. And so I want to do a quick practice problem on this. And so we want to use the graph below to determine the intervals where this function is increasing, decreasing, concave up, and concave down. I'm going to throw in a bonus if you have time. Also mark where this graph is positive and negative, because that's the third category. So I want you to take a minute, sketch out this graph, and just kind of mark on it. Where is it increasing? Where is it decreasing? Where is it concave up? Where is it concave down? And then if you still have time, where is it positive? Where is it negative? Right? Because we want to get really good at looking at graphs and talking about each of these three categories. So I'm going to give you a minute and a half, 2 minutes, just to mark up where you see that happening, just in case you can't see it. This is 1. This is 2. We're counting by 0.2s on this axis. And then over here, we're counting by 0.5s. That's 1. And that's -1. Okay, so take 1 to 2 minutes, mark it up, show where it's increasing, decreasing. If you remember how to use your interval notation, you can go ahead and write it that way, but we'll go through that together in about 2 minutes. Okay, take about 30 more seconds. So let's start with increasing and decreasing. So again, we're looking for where the graph goes up and where it goes down. So let's start with increasing. So I notice here that my graph starts going in the upward direction till right about here. Okay, so here I am increasing. And if I was going to notate this, one of the things I notice is that this changes at about 0.5. So the way I'm going to do this is I'm going to write 0 less than x less than 0.5. So I'm using open interval notation. Notice that I didn't include the 0.5. The point where we change from increasing to decreasing is considered constant. So we don't include it with increasing or decreasing. Okay. I also notice I'm increasing over on the second part of the graph. So right about here at 1.5, I notice I start going up again. So I'm increasing here. So here I'm going to say 1.5 and 2. So I'm going to use open interval notation. And then in between those two increasing spots, I see that I'm decreasing in between. Right? Because I'm going down the whole time from left to right. And so here we have 0.5 less than x less than 1.5. And so my three intervals make up the whole entire thing, right? I'm either increasing or decreasing. And these points where I change, they're going to have specific properties and we're going to learn more about them. But for now, we're just going to say, hey, we're constant there. So that's increasing, decreasing. The next thing I asked you to think about is the concavity. So looking at this graph and trying to visualize from 0 until just about 1, my graph bends downward. It looks like a hill. So I'm going to be concave down from 0 to 1. And again, I'm going to use open brackets because the point where we change concavity, okay, is going to have a special name, and it's not concave up or concave down. Well, I'll tell you, it's called an inflection point, which we're going to learn more about later in the course, but it's not concave up or concave down right here. Okay, that's the point we change. And then to the right of that point, we see that our function bends upward. Okay, so it looks like a cup. So here we are concave up, and that happens, it looks like between 1 and 2. Okay, now finally, if you had time for this, I asked you to think about where this graph was positive and where it's negative. So here, for the portion of the graph that's above the x-axis, that's going to be positive. And then the portion that's below is going to be negative. So the positive part of the graph happens for x between 0 and 1. And the negative portion of the graph happens for x between 1 and 2. And again, we're not including the 1 because at 1 it's 0, and 0 is not considered positive or negative. But positive or negative has to do with whether the graph is above or below the x-axis. So those are the three types of ways we use to describe graphs. This is going to become really important in the work we do, but just as a reminder, we are going to be using average rate of change to talk about concavity. But if we have a graph, you can look at the physical features of the graph to also talk about concavity without having to calculate average rates of change. Okay, so as I mentioned, there's two types of rates of change. Most of the time we spent doing average rate of change, but there is a second type, which is called relative change. We don't use this nearly as much. We do a couple of examples here and there, but it's important that we understand the difference, okay? And so to give you an idea of why we might want to consider relative change for some particular problems, I will present to you this example, right? If you go out shopping and you receive a $1 discount on something you've bought, is that a good deal, right? And to answer that question, you really depends on how much the product costs. So consider this, scenario one, you're gonna buy a new car, $25,000. You go to the dealership and they offer to give it to you for $24,999. So they're gonna save $1 on this really expensive car, right? So that $1 is not a very good discount, right? I think we can all agree. Now, let's consider another scenario where you're going to go and you're going to buy a coffee at Dunkin' Donuts, and it's going to be $2.64. Today, they're having a promotion, and they're going to sell it to you for $1.64. So again, you're saving $1, but now the savings is more substantial relative to the price, right? So when we talk about discounts and prices changing, this comes up a lot in business. We often want to think about how the change happens in comparison to what the original amount was. Same thing with population, right? If we're talking about a population changing by 1,000 people, if you have a tiny town that only has 500 people, that's a huge change. If you're talking about New York City, right, 1,000 people coming or going is not a big deal. It's relative to the original size. So the way that we calculate and consider this is with a slightly different formula. So the relative change, which we also sometimes call the percent change, is used to compare two quantities while taking into account the size of the numbers being compared. Okay, so our formula looks like this. So P1 minus P naught. So whenever you have a P and then a little zero to the right, we say P naught in math. It looks like a knot, I guess, on a tree. Is what, I don't know why we use knot. But what P naught just means P sub zero. But anyways, we do the change and then we divide by P naught. So these numbers, what do they represent? So P1 is the new amount of whatever it is that we're measuring. And P naught is the original amount. Okay, so what we're doing in this calculation is we're looking at how much the amount changes. So P naught minus, or P1 minus P naught, how much did it change, divided by the original amount, because that is going to tell us the percentage by which we changed. Okay, and that's going to help us understand whether or not the change was significant or not. Okay, so let's look at this formula with the two examples we just talked about. So scenario one, we're buying a car. Okay, the car cost $25,000, so that's the original amount, and the dealership offers to sell it to you for $24,999. So that's the new amount. Okay, it was always $25,000. This is the discount you're getting. So if we want to talk about how meaningful this is, we want to find the relative change. So we do P1 minus P naught. So 24,999 minus 25,000. And then we divide that by the original amount. So 25,000. Okay, when we plug this into a calculator, we're going to get a decimal number out. We're going to get negative 0.00004, I believe. So once we get out our decimal number, we are not done. We have to do two things. We need to convert it to a percentage, and we need to consider whether or not our solution was positive or negative. So to convert a decimal to a percentage, we move the decimal point over 2 places, okay? So when we do that, we are gonna get 0.004%. And then if the sign in front is negative, we add the word decrease. Okay, so the price decreased by 0.004%. That is very, very small. If this was a positive number, we would say something like increase or growth. Okay, so we convert the sign into a word to discuss what's happening. So we can all agree that a 0.004% discount is not very good. Okay, let's consider the same thing now with our coffee. So the coffee usually sells for $2.64. Today we're going to get it for $1.64. So we want to determine the relative change. Okay, so I want you to take 2 minutes, 1.5 minutes, and try to use this formula to see whether or not this deal we think is a good deal by looking at the relative change. Okay, so try it out. I'll give you 2 minutes and then we'll go through it together. Okay, take about 30 more seconds. Okay, so here our original amount was $2.64 and our new amount was $1.64. So when we put this into our formula, we're going to be doing 164 minus 264 divided by 264. So again, because the price is decreasing, we're expecting something negative. We get negative 0.3788. And now we want to convert this to talk about it. So to turn it into a decimal, we move the decimal point over 2 places, 37.88%. And now because it's negative, this was a decrease in price. Okay, so obviously the 37.88% decrease is far more substantial than the first one. So we can see that relatively the $1 discount made more of an impact on the coffee, which you may have suspected. Now, I do want to mention a couple things about Wiley because it's a little bit picky about these types of problems. First, you need to pay particular attention about whether they're asking you for the decimal or the percentage. So if it says percentage after the entry box, you have to convert it. If it doesn't, then you don't, unless it tells you to convert it to percentage. Similarly, if it doesn't include increase and decrease, then you may need to include the negative sign in your answer. If it does include a decrease, then you don't include the negative sign. Okay, so you need to be extra careful about both those things. Okay, there's 2 examples on this. If you want to see them, you can click on the asynchronous lectures in Moodle, but they're the same types. Good luck with all your stuff this weekend, and I will see you guys on Tuesday.